Welcome, everyone. Thank you so much for joining us today for the Grasp on Robotics talk series. I'm Lingjie Liu. I'm a faculty host for today's talk. Before introducing our guest today, as a quick reminder, previously recorded talks that can be found on our YouTube channel and website. You will have an opportunity at the end of the talk to ask your questions. But if you have a question during the talk, please raise your hand so I can bring you the mic. Okay, then it's my great pleasure to introduce our guest, Roni Sengupta. Roni is an assistant professor of computer science at UNC Chapel Hill. She leads the spatial and physical intelligence swing lab, building spatial AI models for the physical world. Her research lies at the intersection of computer vision, graphics, broadly in 3D vision, computational photography, with the special focus on solving inverse graphics and physics problems with applications in visual content creation and editing, telepresence, AR, VR, robotic perception, and 3D medical imaging. Previously, she was a postdoc at the University of Washington. After her PhD from UMD, she is the recipient of the New and Early Career Trailblazer Award from NIH. Her work on background matching received a Best Student Paper Honorable Mention at the CVPR 2021. And actually, this series of work has have been adopted by many companies, including Microsoft, Interstate Studio, and Lenovo. Actually, I'm also a big fan of the series of background matching work, and also her early work in inverse rendering. And I want to learn more about her recent work. Yeah, thank you for for visiting us at Penn, and I look forward to your talk.
Thanks, Lingjie, for the invitation. Thanks, Lingjie, for the invitation. It reminds me, roughly 9 years ago, I was on your side of the stadium here. We used to have something called Mid-Atlantic Computer Vision Series. Costas was hosting this seminar series. I was a graduate student at University of Maryland. It was one of the cold February days. We huddled into one Airbnb somewhere over there, all the grad students. We came in the morning, set up our posters. It was a very exciting time in 2017. Computer vision is starting to work, and we are all kind of excited about it. So I will kind of start with a nice quiz that I always do in my class. It's kind of my favorite one. Looking at this shape, I want you to say if this is a shape of a crater or if this is a shape of a dome. So crater is something that goes inside, and dome is something that comes outside of the surface. So how many of you think this is an image of a crater? We can raise our hands. Okay, 1, 2, not too many. How many of you think this is an image of a dome? Okay, majority dome, that's good. Let's take a look at another image. How many of you think this is an image of a crater or if this is an image of a dome? Team crater? Okay, a lot of people switching sides. Team dome. Okay, few people staying there. What if I said these are exactly same images, just turned 90 degrees upside down? And in fact, the image on the right is the actual image of Victoria crater in Mars. And the way you perceive this image is actually what most humans would do. And why do we do something like that? Because as humans, we expect sunlight in images to come from the top. So whenever we take a photograph, we usually have sun or any light sources at the top of the image, and that's lighting the object. So if you look at the background, first image on the left, you will see there's a lot of highlights at the top of the image, which makes you feel like the object is kind of coming up. On the right, you have a lot of cast shadows on the floor, which makes you think that the object is going down. So although we can understand shape, it's very limited by our prior assumption of what lighting is in the scene. But is it only the assumption of lighting that makes us feel something about shape? Can we play with other physics that makes something look different than what it actually is? And this is my favorite example. This is makeup, and this is a specific thing about makeup called contouring. So if you're unfamiliar with what contouring is, it's usually a pigmentation that is darker than the color of your skin, and you put the pigmentation in the right shape and order, and you blend it in the right shape and order, and it can give very different meaning to what is the shape of your face. You want those strong jawbones, you can make your contour in the jaw, and it will make the face look very, very different. So it's another very interesting play on the underground physics. So humans have some kind of physics perception. This is kind of often ambiguous since we rely on a lot of basic priors to understand what shapes are. And this is not a new problem in computer vision. I would say it's one of the long-standing problems, going back to the earliest paper of Barrow and Tannenbaum from 1978, which is recovering shapes, recovering intrinsics from scenes, to this very famous paper on Horn and Brooks in 1980s, and this very famous NeurIPS paper in 2000 from Bill Freeman's group. And this was history, and then I started kind of like my PhD, and this was one of the most popular paper when I started my PhD called Shape Illumination Reflectance from Shading from Barron and Malik in 2012. And it showed that you can actually make these algorithms work for real images, not those cartoonish line drawings, by using a lot of handcrafted priors. So if you read this paper, if any of you have read this paper, it proposes a lot of different kind of handcrafted priors to make this problem work. So what happened after 2012 is we simply replaced handcrafted prior with data-driven priors or neural networks, and that's what most of the research field is now about understanding physics. So the kind of physics I'm talking about, at least in my research group, is the following. Given a video of an object doing something, we want to decompose it into different components. One of this component is understanding the shape and the camera parameters. The other components is understanding the physics of object and light interaction, which can be material reflectance and lighting. The third component is understanding the physics of deformation, which is how the object deforms when a different kind of forces are applied on it. And the last component is how does this object and the background kind of interacts together and creates this whole thing. In fact, all of these examples are completely generated by computer graphics. So you can imagine that I can create everything on the right-hand side. I can do then rendering and simulation, and I can create a really nice looking video that looks something like this. So the problem on computer graphics side is kind of well solved, but how do we solve the inverse problem is the research that we are interested in. And this technique has a lot of application from content creation, telepresence, AR, VR, robotics, medical imaging, robotic surgery, and you will see a glimpse of some of these experiments throughout the talk. So why is this problem hard? The problem is hard because it's extremely ill-posed. You technically have one observation, which is videos, maybe a couple of different poses, and you are trying to predict all of these components from just a single observation, which is mathematically an ill-posed problem, and we have to rely on a lot of priors to solve this, and our priors usually come from neural networks. But there is another reason why the problem complexity changes is how we model each representation. What is the right way to represent each of these components? So for example, let's take something like material reflectance and think it of how we can represent material for human faces. We can start with something as simple as an albedo. This is very simple. Optimization and inverse processes are easier when you have an albedo assumption. But real objects and real human faces rarely just have albedo. So if you start to add more and more complexity, like add specular highlights, add subsurface scattering, the complexity keeps on increasing. And as the complexity of the representation increases, the problem becomes even harder to solve. So that's been the major challenge in solving this kind of problems. So in my lab, we take two different approaches of solving this. One is sort of an explicit physics approach where you explicitly obtain all these components. So it's like a reconstruction for all of these components. And we also take an implicit physics approach where you do not really care about reconstructing the scene, but you want to change some of the physical parameters. For example, you can change lighting of this scene and create a new video with different lighting. Or you can change some of the deformation parameters of the scene, and you can create different things, or change the camera pose. And of course, the later part involves a lot of generative models. So in this talk, I will try to give an overview of different works we have been doing in this space, both in implicit and explicit inverse physics. We'll start with something on explicit inverse physics type. As Lindsay said, my group has been doing a lot of different works on inverse rendering over the last couple of years. Unfortunately, I'm not going to talk about this today. We have been also doing a lot of work on inverse deformation. That has been a little bit of a recent thing. But instead today, I wanted to focus on something interesting that we have been doing that requires both inverse rendering and inverse deformation, but for the purpose of endoscopic 3D reconstruction and localization. We had two recent papers, one in ECCV and NeurIPS, and I'm going to talk about what this problem is and why people in computer vision community should start finding interest in solving things in this direction. So what is the problem of endoscopic reconstruction? If you're unfamiliar, endoscope is an object which has a light and a camera source attached together. It's put inside your body, either through your mouth or through your anus. And it's usually used to do upper airway or lower airway bronchoscopy, or it's used to inspect your gastrointestinal tract for many different reasons, from lung cancer biopsy to detecting airway abnormality, for cancer screening in colons, for polyp detection. And as you can see, there is roughly, in my estimate that I saw from NIH stuff, is 20 to 30 million endoscopy procedures are done annually in the United States alone. However, talking to a lot of clinicians, these procedures are largely qualitative. That means clinicians often look at these videos and decide what's the size of the polyp or where is the biopsy target. And there is very much lack of a quantitative measurement that physicians can use for solving this problem. So here is some of the specific examples that I am working on with my collaborators. One of them is robotics bronchoscopy biopsy. In this case, you want to have a robotics biopsy happen by putting a bronchoscope navigate through your airway to go to the right location and perform some kind of a needle-based surgery. So to do this needle-based surgery, you need good amount of camera tracking in the airway, which is deforming. Then we have clinicians that tries to have some kind of a 3D visualization or guidance during this different kind of endoscopy, which is also kind of missing now. And finally, we have clinicians that are interested in detecting different airway abnormality, whether this is measuring the cross-section area or diameter of the airway, and measuring how the breathing deformation changes over time. And they're specifically interested in doing this on pediatric population, which you cannot do multiple ionizing radiation through CT in pediatric population. So there is a lot of clinical needs that I found myself in being at UNC, which is a big medical school. And so I asked myself, what's the fundamental problem behind all of this clinical application? The fundamental problem is a very well-known computer vision problem, which is, can we reconstruct 3D shape, texture of the object, the deformation field in case of airway, and the camera pose. And what I observed while starting to work on this problem is state-of-the-art 3D computer vision problems like monocular depth prediction, pose estimation, SLAM. They all struggle really on this kind of scenes. And why is that? One of the reasons is really a lack of strong geometric features. If you look at these videos, there aren't that many geometric features that you can utilize, unlike indoor and outdoor scenes. So foundation models that you train on indoor and outdoor scene has a huge generalization gap when you apply them directly on endoscopic videos. On top of that, the lighting in this scene keeps on changing constantly. If you are a self-driving car in outdoor scene, the lighting is relatively static. It doesn't make any drastic changes. But here, as the camera moves, the light moves, the shadows change, and that makes all the SLAM algorithms fail. There are really strong reflections that come out of mucus layer, and it's not just specular reflection. There is a lot of subsurface scattering and other physical properties which confuses the algorithms that you work on that. And lastly, the organs deform, maybe not so much in colon, but when you have an airway and you are breathing as the bronchoscopy happens, there is a significant deformation happening here. So for the purpose of the talk, I'm going to focus on specifically on solving two of this problem, that is lack of strong geometric features and handling dynamic lighting in this environment with a focus on colon. And the key idea in our method is, can we sort of leverage and model the near-field reflection of light as some kind of photometric feature for 3D scene understanding? And I'm going to talk a detail about what do we mean about leveraging near-field light reflection for 3D understanding. But I want to kind of talk a little bit about generalization of this kind of techniques. Although we build it for endoscopy environments, there are actually many other robotics environments where you often face the challenge of dynamic lighting. Whether this is subterranean robotics or search and rescue robotics, we often see a light source and a camera co-located together, moving in the scene where there is no other external light sources. And traditional SLAM algorithms are not built to handle this kind of static light in a dynamic lighting condition. So let's quickly review what a traditional SLAM algorithm does. It usually has two phases. There is a tracking phase where you optimize the camera parameters, and then there is a mapping phase where you optimize the 3D map, a little bit of the camera parameters also, and then you kind of like iterate between this. So it's an alternate optimization between tracking and mapping until convergence. And the optimization is largely driven by what is known as a photometric bundle adjustment loss, which basically says if I reconstruct the 3D map and if I localize the camera and then if I render them into an image, the loss would match the image that I captured. So it's really relying on a photometric loss. And since this is a highly non-convex optimization, we often initialize this with some kind of a depth initialization model, like foundation model for monocular depth initialization. So in our work, we make two significant contributions to this. One is replacing the depth estimation to something that is focused more on endoscopy and something that can utilize lighting as feature rather than relying on geometric feature. And lastly, we change the fundamental bundle adjustment loss to model the dynamic lighting that happens in the SLAM environment. So I'm going to first talk with the dynamic lighting component, and then I'm going to talk about the monocular depth estimation. So for sake of easy purpose, let's assume the scene is represented with a set of Gaussians. However, the methods actually hold for any neural rendering-based geometric representation, like NERV. But for now, let's focus on the scene as a set of Gaussian, and you have these cameras. And in a traditional Gaussian splatting-based SLAM framework, you have a color rendering loss and you have a depth rendering loss, where each of the Gaussians have some color and opacity that you are optimizing. Then you render the color and the depth, and you calculate the depth and the color rendering, and you combine them together as your photometric bundle adjustment loss. So the color rendering loss is your image reprojection loss or photometric bundle adjustment loss, which measures the mismatch between the original image and the image rendered with the 3D reconstruction. However, this photometric bundle adjustment loss makes one assumption, which is the color that you have for each Gaussian is static and does not change as the camera moves. So it assumes that the color is multi-view consistent, which means if you move your camera, whatever is the color parameter on top of the Gaussians usually don't change. You can add components to handle for specularity, but the diffuse color component of that model do remain constant. However, in practice in endoscopy, the color does not remain constant because you have a near-field light effect. So what does that mean? If you have these Gaussians, and these are the surface normal of the Gaussian, and you have a collocated light and camera, this means the color received by each, the lighting received by each Gaussian should be proportional to the distance and the orientation of the 3D Gaussian. So if a Gaussian is closer to the camera, it should receive a lot more light. And if the orientation of the Gaussian is facing the camera, that means the normal of the Gaussian is exactly in the direction of the normal of the camera, it should receive a lot more light. So we know that physics happened. So this means the Gaussians on the left should receive a lot more light than the Gaussians on the right. And as the camera moves, this should change. Now, the Gaussians on the other part should receive a lot more light. I'm not sure why this is not showing up on the Zoom screen. Let me stop sharing and try again. Okay, it works now. Sorry. Okay, so when the frame moves, when the camera moves, now the lighting pattern ends up changing based on which Gaussians are closer to the camera and which Gaussians have normals that are closer to the camera. And we can then encode this rendering function. We can then physically model how the rendering works using some specific near-field light rendering. And in fact, this is just a simple one-line change in the Gaussian splatting kind of based on SLAM framework. So you have a color rendering loss. Since with dynamic lighting, the color rendering loss is not constant, what we do is we model the color rendering loss as a combination of albedo and per point shading or per pixel shading. So rather than just assuming the Gaussians have a color that does not change, we assume the Gaussians have an albedo that is constant, and then there is a shading term that can be physically computed, not optimized, based on the relative distance and orientation between the Gaussian and the camera. And with that, every other component of the Gaussian splatting by SLAM remains the same. So in a way, you can actually use this algorithm to any neural rendering based SLAM framework. In the paper, we had it applied on multiple algorithms, and it's a simple change in how the color is being rendered to compute this. So in fact, the change is only located in this region. Notice in practice, this is only calculating the diffuse components of the lighting. It's not handling any specular reflectance. So what we do in practice is we detect and remove any specular components from this color rendering loss. And towards the end, I will say you can probably model the specular components. There is no need to reject them. But modeling specular component is not a simple change in term, and it's add a lot more complexity to the optimization. So what we noticed in practice is having specular reflectance model makes the optimization really hard to converge in quick amount of time. So we didn't go into that direction for now. So how do we model the shading term? We model the shading term using this simple idea that I'm describing the idea on images first, and you can then extend this into a 3D. Suppose you have each pixel of an image that is denoted by X, which is a point on the surface, and P is really the location of the camera or the location of the light source. That means the shading at each pixel would be a factor of the lighting direction, which is simply the direction that you calculate between the point and the light, and the factor of the light attenuation, which is the distance between the light. So it takes an L2 square loss. There is also some angular attenuation that you can do. So you can combine the lighting direction and the lighting attenuation together to get what we called per pixel shading. This basically says how much light should each pixel on the image or each point on the surface should receive. And then you take this per pixel shading and albedo, and you multiply them together, and you get the reconstructed image. Notice how we block out the regions of the specularity, because in those regions, this simple combination is not going to hold true. And if we calculate sort of the error between the ground truth and reconstructed image, we see that this per pixel shading-based model holds true for most regions, except regions where you have strong cast shadows or high specularity. You can't probably see it very much, but there are a few lines here and there for high specular region and cast shadows region. So that's how we do it. But in practice, we don't compute it on the image directly. We compute it on top of the Gaussians. I just described it as doing it on the image to keep it simple. In practice, every Gaussian receives a different amount of shading term that is computed using the following math. Okay, so we integrate it on many different SLAM pipeline. For now, I will just show on the MonoGS SLAM pipeline that was pretty easy to incorporate things into. And when we initialize this with ground truth depth to begin with, and once we bring in the NFL-BA loss, we see that the tracking error and the mapping error improve significantly. For most of the endoscopy purposes, the tracking error in translation ends up mattering a lot. 1 degree, 2 degree rotation error is not super significant, but the exact tracking error ends up mattering a lot. And then we replaced the depth estimator with a state-of-the-art depth estimator at that time, DPT hybrid, and we saw it also has improvement in performance, but obviously the performance degrades because you do not have a ground truth depth initialization. Which will bring to the second part, which is what happens if we can come up with a better depth initialization to bridge the gap between a ground truth depth-based tracking and predicted depth-based tracking. And that takes us to the second contributions of this line of work, which is the PPSNet. It's much more heavy machine learning, so I'm probably not going to go into too much detail. But what we did is we took a foundation model like Dino V2 features, and we fine-tuned these Dino V2 features on endoscopy videos. That's the first step. And in the second step, we design a refinement network that actually encodes this lighting variation pattern. So it's not just few layers of additional neural networks. It has some extra input it takes about the lighting and shading terms. And finally, we have some self-supervised fine-tuning on real data that allows us to get higher quality result. So that's basically what we do. Train on endoscopy videos, explicitly model the lighting and give them as input in this PPS term. So all this PPS stuff that we have done, we give this additional components as input to the neural networks to see how much it can utilize it. And here is some results on synthetic data. These are pretty, I wouldn't say it's synthetic data, it's more of a phantom data developed by Johns Hopkins, actual like phantom model with physical robot going through it and capturing the scene. And these are some of the performance of state-of-the-art models at that time. And when we just do supervised fine-tuning with Dino V2 features on this data, we see a good improvement, but still quite a big gap. And the refinement network that utilizes the lighting-based features leads to much better improvement in the depth performance. And these are some of the real results on clinical data. There is no ground truth, so obviously we have to judge the quality ourselves. But as you can see, the first one is a particularly challenging one. There is like some areas that kind of goes down and comes up, and we have a little bit better reconstruction in those part of the scene. So now we take the PPSNet predicted depth, we incorporate them into the SLAM pipeline, and we saw the improvement helps in tracking and mapping. It gets close to 2 millimeter tracking accuracy and less than 1 millimeter mapping accuracy with predicted depth. And that's kind of the state of the art at that point of time. And I will show you some of the video results of how this works in practice. So the middle column is the baselines, which is mono.js in this case, and the right columns is our reconstruction and our camera trajectory. So this is another sequence. So while this can be applied on endoscopy videos as the main motivation, we did also some interesting real-world experiments where scenes have been captured with just a collocated light and camera. Basically, take your iPhone, turn on the flashlight in your iPhone, go about in the scene and capture the scene. From the iPhone alone, you can get reasonable odometry data, which is our ground truth camera trajectory. And as you can see, even in these scenes, if you just do photometric bundle adjustment, the camera trajectory is significantly off. This is not endoscopic scene. You have good features, but just the fact that you have strong dynamic lighting that keeps on changing makes tracking significantly harder, whereas the results that we were getting in terms of the tracking were much more closer to the original scene in that way. Okay, so that's kind of on the endoscopy side of things that I wanted to talk. I will finish it off with few key takeaways, and then I'm happy to take question on this part before I switch to something else. So in my opinion, it still has a huge clinical demand and relatively unsolved in practice. There has not been huge breakthroughs where this can go into clinical trial kind of a phase. And what I observed is simple extension of 3D vision algorithms on medical imaging does not work. And we really need to innovate new computer vision techniques, especially to handle challenging lighting, challenging appearance, and deformation patterns that is present in endoscopic videos. So in a sense, it's a really hard case problem for inverse rendering research, people who love to work on high specular reflectance, subsurface scattering, global illumination, near field lighting. We used to do this research on objects and indoor scenes. And I would say on objects and indoor scene, all of these hard effects are probably 10, 20% there. And if you look at an endoscopic scene, these effects are 50% there. So if you really want to build algorithms to tackle all of these hard computer graphics lighting cases, endoscopic environment is one of the great environments to build those algorithms and realize how good they are. So looking into the future, what we are kind of trying to do next is, as I mentioned, we mainly still model the diffuse reflection. We ignore all other aspects of lighting, like subsurface scattering, specular highlights, and we mainly ignored it because it made the optimization process really difficult to track. So I think in future, being able to invert the full light transport that happens inside the endoscopy could really help us a lot. So that's one direction we are looking forward to. The other direction is making this work on airway. So these results are still on colon. Colon is reasonably static, makes it easier to work, but airway is not. So we built an airway endoscopy simulator using sort of 3D slicer and blender. And as you can see, maybe it's a little bit dark over here, but the airway deformation is actually significant, and the whole surface kind of moves up and down as you inhale and exhale. So predicting airway deformation, static 3D shape, and camera pose still is a very difficult problem to solve. And I think there is also a role for improving simulation environment, because one of the challenges here is clinical data don't have so much ground truth. There isn't that much clinical data. We have to rely on simulation data to develop our machine learning algorithms, and simulation data has a huge sim to real gap. So how do we improve this gap by combining both graphics and generative models is something I'm kind of interested and looking forward to. So that kind of finishes this part of implicit inverse physics. We're doing good on time, so I'm happy to take questions that people may have in this direction. Yes?
I didn't miss this, but how did you estimate the specular reflection in the...
We don't. So what? Oh, yeah. So you basically have a threshold on the pixel intensity beyond a certain region, and if they have like a small segmentation region, you just remove it. So very simple way of doing. Yes.
One work, I try to understand why the spherical harmonics of the radiance field, like infer or Gaussian splats, are not sufficient.
So they were sufficient to handle the specular changes, but not for the near field diffuse lighting. So we were mainly modeling the near field diffuse lighting. The spherical harmonics on the Gaussian can enable you to change the reflections and the specularity, but doesn't really change the diffuse shading itself, because that's the diffuse shading is the fixed term, and then you have all of the high frequency components.
In the original rendering in different papers from physics, they have a diffuse lighting component on them. So this would be applicable, but we'll use the full rendering without ignoring scattering and.
I think it would be applicable. I think there are actually some old papers from CMU who have looked into how to model light propagation in endoscopic environment or tissue surfaces. But when I looked at those modeling function, they seem highly non-convex. So when you put them into this optimization framework and try to optimize, that's where we got stuck. I still think it's applicable. It's the question of how you make the optimization tractable as you increase the complexity of the light modeling. Yes.
There's absolutely no key point tracking here. It's only the loss function.
Yes.
Yes.
Yes. Yes.
Beautiful work. I just had actually a question about specularities. It seemed that combining your insight about the fact that you have moving light here with the specularity reflection should give you very, very strong normals, at least in particular locations, and then utilizing the motion should give you.
I agree. That was the insight, and we wanted to get to that. And what we realized, at least in that paper, is it increased the complexity of the optimization, because now you have like a BRDF term that you are also trying to estimate, say, the roughness parameters, or, I mean, fog model probably wouldn't work, so you're trying to predict the SVBRDF parameter on each of the Gaussian, render it, and optimize. I think it's doable. I think it just needs another iteration to go at that level.
Yeah, I'm not thinking detail with you, but even just thinking about it as in terms of identifying peaks in your specularity thing, I'm using rough normal estimate.
Right. Yeah, no, that's something we can look into. What I have to look is how much of this reflections is coming from direct illumination versus how much is also added by global illumination, because you have a lot of interreflections happening, subsurface scattering happening. So even if you're seeing the specularity there, it doesn't mean the normal is exactly aligned to that. Actually, we looked into that. What we looked into is looking at the specular region that we are masking, looking at the normal angle, and seeing the correlation of the normal angle with the camera. We observed that correlation was roughly 80%, which means it's a strong signal, but not like completely strong signal because of interreflection specularity. And at that point, we thought of like, if we put that, it may take the optimization in any side. It will be a little trickier to handle that. So we didn't end up going. But there might be something simple to do on that direction. Thanks.
There is one question.
Yes. Let me try to see if I... Oh, I can't see the Zoom questions for some reason.
Oh, I think someone just raise her hand.
Oh, okay.
Maybe after the
How do I...
speaker. Uzano, can you hear us? Okay, maybe.
Okay. Okay, if there are no other questions, we will have time at the end to have questions. So we switch gear a lot from like explicit physics to more generative models. And we have been doing a lot of exciting works in different aspects of it, from changing lighting to changing video effects to changing aging effects with diffusion models. I'm going to sample a little bit of all of this work. We'll not have time to go into very detail of each of this. So I will start with this lighting work of ours called Scribble Light that was published in last CVPR. You have a room of an indoor scene, indoor image. You want to change lighting. So white means turn on light in this region. Black means turn off light in these regions. So you can then, using simple scribbles, change a scene from a nighttime scene to a daytime scene. I would show it another time because it kind of went fast in the animation. So you can see you can change this nighttime scene to a reasonably daytime scene with a high quality rendering. And then you can actually keep on iterating this to go to much more fine-grained lighting effects that you want to create. So now we'll start by turning on one specific lamp. It turns on that specific lamp, but also renders the global illumination below the lamp. Then you can create a strong highlights on the bed and strong shadow on the other side of the bed. This is kind of saying that the sun is kind of coming angularly to the room and hitting the room in a way you have strong sunlight. And finally, I wanted to see what happens if I want to create a cast shadow of this bar that you have, and it can render this cast shadow reasonably well. So the idea was, with simple scribbles, can you change lighting of an image without any other external input? And so how would you kind of tackle this? Back in 2025, we had control net, diffusion models. So the basic baseline, the naive way of doing it is add the image as in the diffusion component, add the scribbles to the control net, and let's see what happens with that. So that's the baseline design. And when we applied that, we got a result that looks something like this. As you can see, it does turn some of the lights on and off, but it also introduces a lot of artifacts on the scene itself, both in terms of the geometry and the texture of the scene. So we noticed that it does not really preserve the albedo of the scene in any real way. So then we thought like, okay, it probably because We have just a control signal. It's not preserving any of the intrinsics in the image. So what we ended up doing is we took the albedo and instead added the albedo directly to the diffusion model. So now having the diffusion model run just on the image, we have the diffusion model run jointly on the space of image and albedo. So it's modeling a joint distribution of the image and the albedo for this purpose. And when we do that, simply add the albedo to the diffusion model, retrain the diffusion model. The result improves pretty much. We have much more reasonably clear picture. The lighting looks good, and we thought we are done with it. And maybe if we submit to CVPR, people will say no novelty. So then what we realized is if we actually start looking into the details of the rendering, start zooming in, we started to see that although when you have a zoom out picture, things looks fine. When you start to look into the details, maybe it's a little dark from this angle, the chairs don't make sense. The shapes don't make sense. Like on a grand scheme of things looks fine. As you zoom in, things starts to look broken. And that made a question that is really the scribble and normal, just concatenating them, adding them to the control net, is that really the best input to provide for this kind of a problem? Is it something that can control the problem reasonably well? So what we ended up doing is our intuition was if you just let the network take all of these inputs, it probably doesn't learn what it is needed. What if we force the network to pick up what is needed? How? So we take the scribble and the normal as an input. We train an autoencoder, which encodes the normal and the scribbles into a latent space, and a control decoder, which decodes the normal back, but now from the scribble, it actually decodes a shading map back. So what you are creating as a result is, although you have the normal and the partial scribbles, you are now creating a full shading map for that particular image. And as you train, this latent space is now a latent space that truly learns the interaction between the geometry and the lighting. That's the hope, because you have to reconstruct the original shading map. So when we train this, we simply take an input image, we simply perform inverse rendering, not inverse rendering, IID, intrinsic image decomposition. We get the normal and the shading map. And when we add the scribbles, we force this encoder-decoder architecture to kind of complete the scribble into an actual shading map. And whatever the latent space we learn from there becomes the latent space to the control net. And that leads to significantly much better control stability in the results we obtained. So here are some of the results compared to existing methods. Of course, before this method, the other methods had harder time getting fine-grained control. So this evaluation is a little unfair in that aspects, because we were the first one kind of doing this scribble-based segmentation. But still, like for the paper, you have to do those things. And then we had this fun idea of what happens if we provide implausible signals. Like if you provide a signal that is like a scribble that is physically incorrect, and the generative model has to do something, what will it do? And here is an example. There is a sunlight from outdoor. You provide the shadows, but if you see the shadows, they do not align any way to the sunlight that's coming from the outdoor. You suddenly add a scribble at the top to hallucinate something. And if you look at the network image, it does look reasonable. It's not too bad. So it listens to this, it kind of listens to the scribble, but also tries to manage some kind of realism. And it goes somewhere in between, where it ends up hallucinating some light sources outside of the image on the top. Maybe there is a weird lamp at the top that's creating a strong highlight, and it turns off the light from the window just to create some appearance of the cast shadow. So it does some interesting weird hallucination to get it there. So while we required kind of drawing the scribbles out, it's a longer annotation task, we looked into, can we do something that would just say, turn off this lamp and turn on, so in this case, turn on the lamp, turn off the window light, just by text prompt. And we basically use some open source multimodal large language model and semantic segmentation to kind of automatically generate the scribbles from simple textual command. And that can also allow you to relight the scene without having to manually draw the scribbles just from simple text prompt. So I'll kind of move into our next work on kind of generating video effects. This is a pretty new work in collaboration with ILM or Lucasfilm. I'm kind of excited about the demos we are creating about this world. So to give you a background, in visual effects, the way visual effects are created is through something called layering. In layering, you have a foreground that is doing some action. Maybe you are just jumping, I'm just jumping on this. And you create a background which is just a puddle of water. You take two videos, one is me jumping on this board, and one is the puddle of water. You compose them together, and a VFX artist goes in and creates a splash that is going to say how the splash would look like. So any kind of visual effect scenes that you see which have unreasonable things like a big car rolling down the hill, creating a lot of dust, you never actually send a car down the hill, create a lot of dust, and create that kind of damage. What you do is you probably drop a toy cart, something on a small scheme of things, and then you layer it and you create the effects manually. So we wanted to create that kind of a layer effects with generative video model. So I'm going to play over this video, and it has. So there is a foreground of a car driving, there is a background, and if you just have the foreground background, it looks weird. So we wanted to generate effects like generate smoke. And then you can control different ways this smoke can happen. You can increase the intensity of the smoke. You can add color to the smoke. And similarly, if you're jumping on a puddle, you can take two videos, and you can say generate reflection and splash. It will generate a reflection, and it will generate a splash. You can then draw the splash to control the extent in which the splash will be created. You can then compose the foreground and background and replace the background and create different effects like the splash of water or this kind of a dust storm. So I'm not going to be able to talk so much into the details of this work, but if you're interested, I can give a glimpse of what we have been doing there. And it's kind of an archive, and there is a website where you can see all the detailed results of different effects that we can generate as a result of this. So I will go to the last effects that we were working on, which is aging. We have two papers on this series on SIGGRAPH and SIGGRAPH Asia. I'm going to talk about our SIGGRAPH Asia paper called The Aging Multiverse, Generating Condition-Aware Facial Aging Tree with Training Feed Diffusion. The idea is simple. If you have an input image and you want to explore how aging would look as a factor of lifestyle, health choices, and different things, for example, lose hair when you are 50. So this is King Charles. We made him lose hair when he's 50. He's never going to sue us, hopefully. And then we will make him regain hair at 70. And you can explore different life and behavior trajectories that can happen as a factor of aging.
What is the evaluation of this? In SLAM, we can evaluate. How do you?
I will show. Of course, it's not as accurate as a SLAM evaluation. And here is some comparison with existing methods like flow edit or RF solver edit. These are all training feed diffusion models. The idea was you don't want to train anything specific for this task. And then I let this run on my students. I also had it let it run on me, but I never allowed the students to put my pictures into the, I don't want to see that. So I had this done on my students. I still think this is the best result. This is a completely plausible 60-year-old Indian uncle that I can imagine of my students. So he definitely was not super happy, but the result was good. So I was able to come up with something. So that's kind of on the demo. So how do we do it? I still have like 10 minutes. So I can probably go a little bit into the details of what we do and how we evaluate these things. So let's start with one of the very good editing algorithm, in my opinion, is this algorithm called flow edit. It allows you to edit images in the latent subspace. If you're unfamiliar, you might want to read it. I think it was ICCV Best Student Paper or something like that. It's a very interesting, mathematically detailed paper on ordinary differential equations that you might want to take a look at. But without going into the detail, Flow Edit does a very good job at editing, but it often suffers from inversion quality. That means, yes, it's making this person old. It's making, by the way, this is my student, Andrea. I was talking to Kostas about it. So she kindly donated her picture for the paper. So it makes her old. It makes her look 70 years, but not quite the inversion that we needed. So there is another paper which talks about how to fix the problem of inversion editability trade-off, which is often a big problem in diffusion models, that you either end up editing so much that you lose what you originally had, or you edit so little that you kind of preserve what you had, but you cannot really edit it to the extent that you want. So here is the alternate way of doing it, which is RF solver edit. What they say is the transformer blocks in this diffusion model have values, and these values kind of holds the key information about the image. So if you take the values from the inversion block and move the values to the denoising block, it should stabilize the information, which it does to some extent stabilize the information. It has some identity, but it suffers from being able to edit too much. So most of the challenge in this kind of training free diffusion models has been the inability to handle this editing inversion trade-off. So what we do relies on, of course, without going into the detail, relies on this simple observation that the keys and the values of the transformer often hold a lot of information. And one way to handle it is if the keys and the values in the inversion block and the keys and the values of the denoising block are highly correlated, that's good. If they're not highly correlated, just drop them. Like not actually drop them, but suppress them. So the surprising finding was, although you have so many keys and values in the denoising transformer blocks, not all the keys and values are equally important. In fact, dropping things that are not useful, suppressing those things, actually leads to much more stable editing results that you can get out of it. And that was the key insight. Of course, there is a little bit of a math on how we do this editing and inversion, but fundamentally, you can think of we simply take inner product between the key inversion and key edit, and if the inner product is close to 0, we suppress the values of the key edit. So that's kind of the, on a high level, the idea that you only keep things that are highly aligned between the inversion and the editing branch such that those informations is well preserved. So that's what we did on a high level. Of course, the evaluation is the tricky part, but we do have human evaluation and numerical evaluation. I will talk as a human evaluation first, because as a graphics perspective, I think some of the numerical evaluation are not super useful. So first we evaluated it by asking humans to rate the output of each algorithm on a scale of 1 to 5 separately using 3 criteria. One is, does this look like a 70-year person? Does this look like a person whose image I have given as the input? And does this look like a person who has lost hair or who has gained weight, and so on? So we evaluate on these 3 criteria on a scale of 1 to 5. 5 means better. And you can see sort of our results are in that kind of like weak accept to accept zone. And some of the other paper results are more on the borderline zone. And we also then did pairwise comparison where we look at the result from overall point of view. We show our result and a competing method result and ask people to choose what they would choose for this purpose. And obviously, there is a lot of numerical evaluation also. So age MAE and ID similarity are 2 facial recognition algorithms that can take a look at 2 images and say if they belong to the same person or not. And similarly, it can take image of a person and can roughly predict the age of a person. So they're not absolute evaluator, but there are some ways of using face recognition algorithms to be able to see if something is correct or not correct. So that's kind of how we set up this evaluation here. Okay, so I will kind of finish off this image and generative model aspect of physics. And again, kind of in my opinion, or where the field stands, I think we have this image and video generative models have reasonable amount of physics knowledge. I would kind of say like toddler level physics knowledge. And if we look at different kind of tasks where you require some fidelity in the generation of physics and you require high degree of controllability in the physics that you're trying to create, on one axis, you have things like social media reels or AI slops this kind of like fidelity and controllability doesn't matter so much there. I mean, as long as it looks realistic, reasonable, no one is going to judge you if the ball is bouncing at the correct length or not. These are people look at their mobile phone for 5 seconds and it doesn't matter so much. And currently our models works really well, and that's why we have so much AI slops. Somewhere in between, there is this whole idea of using generative models for world model. It has started to show some promise, and I do think it will be solved in future. It requires more knowledge of physics than AI slops, but also it's not clear if you need absolute high fidelity of physics compared to applications like digital twin for science, engineering, or healthcare application. So for example, if I'm creating a digital twin on how a lungs should operate and how a lung should deform, I would expect high degree of accuracy because someone is going to probably train surgeons on that digital twin or surgical algorithms on that digital twin. So the accuracy of that twin will end up mattering a lot. Same for VFX. Because I've worked with VFX people in Lucasfilm and ILM, VFX artists they can actually say if this looks real or not, if there is weird errors or not. And so they really expect a high level of controllability in this problem scale. And in my opinion, this is still far from solved. And the reason it is still hard is a lot of this physics required a lot of domain knowledge. Just throwing in a lot of data does not help. For example, if you're trying to build a digital twin again of how exactly a lungs operate or a heart operate, you really don't have such good data to be able to build it from multiple kind of millions of data. And finally, I think the representation of physics is still an unsolved problem. Like even talking about how do you represent deformation of objects or the physics of deformation, we have good simulation, but the simulation runs on points. Our 3D reconstruction does not usually use points, they use Gaussians. So it's really not clear what's the best way of having a unified physics representation for all of these purposes. And I think for all of this reason, the problem is still far from solved, and probably in academic environment would be helpful to kind of focus on this models, which probably doesn't require millions of GPUs to solve. With that, I would finish my talk by thanking all of the students that have been the part of the journey, and hopefully many more to come on that axis. Thanks.
Yes, thank you.
Yeah, thank you, Roni, for the amazing talk. Any questions? Yes.
I think I can say here.
Okay.
I was wondering, did you have any like pictures of somebody when they were young and then aged them and then it looked like they were now? You know, like.
Yeah, so we had some of those things in that project also to measure, but because we had some test where we did not use any condition, and say we gave an image of Prince Charles and we wanted to see how Prince Charles' image is rendered now because we now have an image. So we had some of those examples there, but we had actually another project that maybe if I have the video here, whose exact goal was to render those things correctly. Let me see if I can find a nice video there. So this was another SIGGRAPH paper called My Time Machine. But the idea is if you're doing aging on any kind of celebrity like Jackie Chan, you do have a lot of images of Jackie Chan from maybe from 20 years old to 60 years old. And if we use those images, maybe we can build a better model for just that person. So in that project, actually, we rigorously measure if the results that you are creating holds up to how that person looks like now. For example, this is an image of an Al Pacino at 70 years old, and we want to make Al Pacino like 20 years old. These are the other algorithms producing Al Pacino at 20 years old. And this is how he really looked at when he was 20 years old. And then we have our model kind of creating that result, which looks much more closely to how he looked at 20 years old. So this was much more of movie and VFX application, where that higher fidelity ends up mattering more because people would remember how, say, a particular celebrity looks at a certain age.
I didn't even think of that, yeah, all these samples you have.
Yes, yes. So we're basically using all the samples from prior for celebrities to help create a much more personalized models.
I think I've seen those things, you know, like they say on the milk part, this person's missing, and then they age forward because they were like 10 years ago.
Yeah.
I was wondering if they ever compared to see if they got it right when they aged them forward 10 years or 12 years or whatever.
Yeah, so we actually had like a journalist reach out to us. There are actually database of missing children, and there are digital artists who can actually has created like 20-year progressed images of that missing children. So the journalist wanted us to run some of these images through our algorithm and just see how it looks like. Of course, it's hard to validate, but what we saw that the images that we generated and the images the human sketch artist generated ended up being quite a bit different. And it's really hard to say which one is correct because that person has never been found. But what we were able to do in that project is do this generation conditioned on many different factors. Because in 20 years, if you have a missing children, how they would look if they grew up in a very bad environment would be very different from how they would look if they grew up in a normal environment. And I think being able to have these multiple options of how they may look at 20 years old would probably help us kind of identify missing child because you have all of these options now to shoot for versus just one standard options that human can create.
Okay, any other questions?
For the splatting, is it possible, can you get a water type representation of the geometry? Like, are you able to build up a mesh that could be used for simulation? Or is that, I understand that it's used for the doctors to look at it as an image and to do diagnoses on their own, but do you view that as mature enough that somebody could come in and put a simulation pipeline on the back end of it?
So if I understand that correctly, are you saying that from that reconstruction, can you make it into a mesh and have a simulation pipeline put on it? I think not completely yet, because what we observed is the Gaussians especially. So the surface is a watertight surface, but the Gaussians that you end up rendering creates opacity to some extent where the rendering looks okay, but the surface is not any more of a single surface. It kind of has a haze around that object, haze around that surface. So if you convert that into a point cloud, it still looks fine. There are some noisy points, but you will probably need a better algorithm to convert that into a mesh where you can then run simulation on top of the mesh. What we are looking at is there are newer representations where you are grounding the Gaussians with the mesh directly, and you are deforming the mesh. This holds more true for airway because for many airway procedures, you often have a single breath hole CT scan before you start the bronchoscopy. And this is just a static snapshot. But what can happen is from that CT scan, you can create a mesh, and then you can ground these Gaussians on the mesh. And then if you deform the Gaussians, you can deform it with the mesh at the same time. So I think some kind of grounded representation between the mesh and the Gaussian can help you achieve that better than just solving that with the Gaussians first and then trying to convert that with the mesh. Because with the Gaussians, you kind of lose the idea of the surface a bit.
Hello. Maybe a follow-up question is that, what is the main motivation of using Gaussian in this scenario? For example, is it because it's have like a faster training process? Why not, for example, use the more like surface representations in this case?
Yeah, so Gaussian's definitely fast rendering process because with points, you couldn't render the image well. So any kind of image rendering loss was really hard to construct. Nerve-based SLAMs were significantly slow to some extent. This is a SLAM method and it needs to operate on surgery time. You do have big GPUs. You don't need 30 frames per second, but it's somewhat you need 20 frames per second, 15 frames per second. And with the nerve-based splatting, like we ran like nicer SLAM and all, the issue was they're really like not even 1 frame per second. And so they were really slow. Gaussian flatting was fast, but can provide image-based loss. But I don't think, as I was mentioning, I don't think Gaussian is also the right representation for endoscopic surface. I think there might be a question of how do you best represent. I mean, mesh is a good representation, but having mesh into a SLAM framework is also not easy. So that is a question of how you best represent the scene, where you get fast rendering, where you can render an image because your losses are image based, and you can render it really, really fast so you can optimize with it in real time.
Okay. Maybe another question is that because I think like in your first work, it's more like explicitly model everything, right? Why not do this more implicitly? For example, like there is a nerve in the wild that they can decompose like to different components and learn them separately. So to remove some effect caused by lighting.
So are you saying like use sort of nerve in the wild approach to remove all the illumination effect and
Yes.
then kind of do actual inversion?
Yes.
I mean, that's an interesting idea, but one thing that might be like if you're trying to do this for an online procedure, which is like as you are doing the bronchoscopy or endoscopy, you want the reconstruction, then running this illumination normalization first and then kind of doing the inversion would also be not super real time. But for some applications like upper airway, you don't need that to be real time because you usually have this video and then you feed into the video to get a 3D model. In those cases, I think you can think of like some implicit method first to remove the lighting and then obtain a geometry from that. So for those applications, I think that direction might also work. We'll be curious to see how those normalization methods work for this kind of environment because nerve in the wild works, but that's for outdoor scene. The lighting is very different from endoscopy kind of scenes.
I see. Very cool.
Oh, yes.
Thanks for this is really fascinating. Out there coming from the machine.
Have you looked at it particularly for gastrointestinal endoscopy using like narrowband imaging and changing wavelength of light to look to see if you can better sort of render the shape of the tumor?
No, that's a great suggestion. A few other clinicians also mentioned like if you add like a simple polarization filter, you might be able to get a lot more information to it. So we haven't looked into the hardware aspect of it, like changing the computational imaging aspect of it. One of the reasons is, to be honest, when we are writing an NIH grant, it's nice to say all existing endoscopes are like this, and the methods we develop can be applied widely to all existing endoscopes, versus saying, I will develop a new type of endoscope that needs to be launched and to be successful. But I do think there is an opportunity to add simple small sensing or like polarization filter to the endoscope to improve it. And I had few computational imaging colleagues who were also interested. It's just like not enough bandwidth to go there yet. And yeah, but I think it's definitely something worth looking into.
Cool. If there is no other questions, I think we also kind of the time to conclude. Thank you everyone for coming, and please tune in next Friday, February 13 at 10:30 a.m. for our next guest talk featuring the George Konidawis from Brown. And for more information on upcoming events, be sure that follow us on social media and check out our webpage. And thank you very much, and I hope you have a wonderful day.